So what we're going to talk about now is electron configuration and orbital energies. So with electron configuration, this is going to be a way for us to quickly identify the location of all the electrons in an atom and what orbitals they're in. And from those orbitals, we'll be able to get a relative idea of what energies they have, so we can determine things like valence versus core electrons. Okay, so let's first start with just thinking about energies of orbitals. So if we look at a hydrogen atom, we've got the 1s orbital. The 1s orbital is at the lowest energy. It's in that n equals 1 shell. As we go to n equals 2, we can have a 2s orbital, or we can have 2p orbitals. We're going to have 3 of the 2p orbitals. As we go to n equals 3, we can have s, p, and d orbitals. Okay? N equals 1 is the lowest energy, n equals 2 is higher, n equals 3 is even higher. All right? That's with a hydrogen atom. And what we're going to do when we identify where electrons are at in the atom, we're going to fill these orbitals up with electrons starting with the lowest energy. Now if we look at the hydrogen atom, it's neutral hydrogen, it's got 1 proton and 1 electron. So the proton is in the nucleus, surrounding that nucleus is going to be the electrons. So where's hydrogen's electron at? Well, the lowest energy orbital is the 1s orbital. So it's going to be in that lowest energy. So that arrow there represents an electron. Now if we were to add more electrons into this hydrogen atom, we'd continue to fill from lowest energy to highest energy. N equals 1 is a certain energy level. All of the n equals 2 orbitals in the hydrogen atom are at the same energy level. All the n equals 3 are at the same energy level. That's in a hydrogen atom. The problem is, when we go to something other than hydrogen, we suddenly add extra electrons in. Well, when we add those extra electrons, we get repulsion between those electrons now, which changes these energy levels. Okay, so this is for the hydrogen atom only, where we've got just the 1 electron. When we go to a many electron system, we can see that those shells split up. So now you notice n equals 1 is still lowest energy, but now with n equals 2, the 2s and the 2p are not at the same energy levels. The 2s is slightly lower energy than the 2p. n equals 3, 3s is lower than the 3p, which is lower than the 3d. When we go to n equals 4, 4s is actually a lower energy than the 3d orbital. Okay? And 4p is then higher than that. So you can see this change in how these energy levels were distributed. We know how they're going to distribute, how they're going to change, but we're still going to apply the same rules of filling electrons up from the lower energy to the higher energy. So as I fill electrons, start with the 1s. Once I fill the 1s up, I go to the 2s. When we get to the 2p level, each orbital is going to get 1 electron before any of them get 2 electrons. That's Hund's rule. Okay, so everybody gets 1 before any of them get 2. Something called Hund's rule. As we continue to add electrons, once the 2p fills, we'd go to the 3s, then to the 3p, then to the 4s, then to the 3d, and then to the 4p, and so on. Okay, that's how we're going to put electrons in these energy levels, in these orbitals. Now one piece of proof we have of this splitting of these energy levels of these orbitals when we have a many electron system is line spectra. If everything had the same energy levels in it, the line spectra would be all the same. We wouldn't have a difference in these energy levels. But because we get splitting of those energy levels, and there's going to be slightly different splitting, we get different line spectra for these atoms. So if we look at 2 different elements, if we get wavelengths of light emitted that are different, they must have different orbital energies. So Bohr's model of the atom is only going to work in a 1 electron system. It's only going to work for hydrogen. When we get to this many electron system, we're going to get that splitting of energy levels. Right now, we want a simpler way, though, of assigning where electrons are in an atom within these energy levels. Okay, to do that, we're going to do something called electron configuration. With electron configuration, we're going to have to fill these energy levels from lowest energy to highest energy, and we're going to write a shorthand notation where we're going to write n followed by the L value, and then superscript the number of electrons in that sublevel. N being that shell, L being whether it's S, P, D, or F subshell, and then that superscript number is the number of electrons in that. We've seen previously where we've assigned things using an orbital diagram with a box and up and down arrows around it. Okay, we'll come back to that as well. Right now we want to focus mainly on the electron configuration. So we want to keep in mind, I want to fill from lowest orbital energy and fill up to the highest orbital energy. Okay, so I can think about this energy diagram here. I go from 1s to 2s, then to 2p, then to 3s, then to 3p, then to 4s, then to 3d. And keep in mind, the s subshell can hold up to 2 electrons, p can hold up to 6, d can hold up to 10, f can hold up to 14. Now, this is a fairly small energy diagram. One thing to note as we add more and more on, those energies at the top of this energy diagram, they get closer and closer together. Okay, but they're still separate enough where we can see transitions between those. Okay, but we're going to have to fill this from the lowest energy to the highest energy. Now, rather than try to memorize the order in which these things fill, we could do that, but there's other things we can look at in order to know how to fill these in appropriately. All right, one way to do that is if I make this little chart here where I write 1s, followed by 2s, followed by 3s, 4s, 5s, 6s, 7s, all in the first column, and then I write the p's in the second column next to their corresponding n values. So 2p is right next to the 2s, 3p is right next to the 3s, and so on all the way down. And then I do that with the d's, and then I do that with the f's. Notice there's no 1p, there's no 2d, there's no 3f. Okay, that goes back to the principal quantum numbers. If n equals 2, all I can have is L equals 0 and 1. All I can have is S and P. If n equals 3, I can have 0, 1, and 2, S, P, and D. If n equals 4, I can have 0, 1, 2, and 3, S, P, D, and F. Now, when I think about filling these orbitals in, the way these orbitals are going to fill is if I look at these arrows and I go from top right towards lower left, I draw an arrow through 1s. I'd start with 1s, fill it up. It can hold 2 electrons at most, so 1s2. I then go to the next arrow, follow it. I go to 2s. It can hold 2 electrons, so 2s2. Go to the next set of arrows. Next on the list is 2p. P can hold 6 electrons, followed by 3s, can hold 2. Go to the next arrow. I go to 3p, 6. 4s2. Now wait, notice I didn't go to 3d. 4s is actually lower energy than the 3d. So it's not a matter of just 2s, 2p, 3s, 3p, 3d and follow those n values. Okay, we've got splitting of those energy levels. They're going to be at different energy levels now. So we're going to get overlap between those n shells with these energy levels. Okay, so follow these arrows. So I go from 4s, next then I go to the 3d, it can hold up to 10. Then I go to 4p, 6. 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2, 5f14, 6d10, 7p6. Okay? So that's the order in which these orbitals are going to fill. That's the order of their energies. So 7p is at the highest energy level, 1s is at the lowest energy level. So if you ever have trouble remembering what order you fill these in, if you can redraw this chart real quick, remember S is in one column, P's in the next, D's in the next, F's in the next, and then keep them in their same rows, and then draw those arrows going diagonally through them, you'll be able to remember these without actually sitting down and memorizing the 1S, 2S, 2P, 3S, 3P, and so on. Okay, so keep that in mind. So with this, we're going to be able to identify locations of electrons in a given atom of a given element, and this is going to be a simple way to illustrate where those electrons are at without drawing those energy diagrams we saw before. Okay, so let's look at an example of this. So with these electron configurations, they're going to show us what orbital each electron is located in. So in order to write these electron configurations, we've got some general rules. Well, first, we're going to have to count how many electrons our atom or ion has. And then what we're going to do is we're going to keep adding electrons to the orbitals until we run out of electrons, starting with that lowest energy going to the highest energy. Okay, let's look at an example of this. If I take the calcium atom, it's a neutral calcium atom. How many electrons is that neutral calcium atom going to have? Well, it's going to have 20. How do I know it's going to have 20? Well, if it's neutral calcium, how many protons does calcium have? It has 20, right? Look at its atomic number there. Because calcium has 20 protons, if it's neutral calcium, it has to have 20 electrons. Protons and electrons have to be equal. So from that, I know I have 20 electrons. Now I need to write out my electron configuration. Okay, well, all I'm going to do is start with the lowest energy, keep adding electrons until I run out of them. So let's think in terms of this energy diagram. So start with the lowest one, 1s. How many electrons can it hold? It can hold 2 electrons. So I'd write 1s2. I've filled up the 1s level. How many electrons do I have left? Well, I've used 2. I started with 20. I have 18 left, so I can still add more electrons. So let me go to the 2s. That can hold up to 2 electrons, so I'd write 2s2. Still haven't used all my electrons. Let me go to 2p. Now remember, with the 2p, it can hold 6 electrons. So I'd write 2p6. So right now I'm at 10 electrons I've used. Go to the 3s, can hold 2. So 3s2. Next to the 3p, it can hold 6 of them. So 3p6. I'm at 18 total electrons now. I started with 20, I have 18, so that means I have 2 left. So I go into the 4s, put those last 2 electrons, and get 4s2. So my electron configuration for calcium would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay, I just started with my lowest energy, kept adding electrons till I ran out. Okay, but don't forget, we can keep adding even more electrons until we use up all the orbitals. Okay, but that's going to get very, very crowded, and we have to keep those in order. So remember, another way we can do this, we can use our little graph. So if I want to get my electron configuration from this little picture here, I know 1s is my lowest energy. So I start there, 1s2. Next I go to the 2s, it can hold 2. I've used 4 electrons. Then 2p6, I'm up to 10 electrons. 3s2, that's 12. 3p6, that's 18. 4s2, that's my 20. Okay, so I can think in terms of those energy levels filling from lowest energy to highest energy. I can also use this picture to predict that as well. Another way to predict it that will actually be quicker and easier if you get used to doing it this way is going to be to use your periodic table. Right, the way the periodic table is going to work, column 1 and column 2 are going to represent s orbitals. So you can see those are listed as the s block. Now you notice I go 1s, 2s, 3s, 4s, 5s, 6s, 7s as I go down the table. Well, the rows are going to indicate which n value I'm going to use. Another thing to note with the s block, how many boxes are in each row? Well, there's 2. Why is there 2? Well, because an s subshell can only hold 2 electrons at most. It's only got 1 orbital in it. Okay, so we're going to have 2 blocks. So each box is going to represent an electron. Let's jump over to the far right where we get to the p orbitals. Notice those rows, still 2, 3, 4, 5, 6. With the p block or the p subshell, I've got 6 boxes. Why are there 6 boxes? Well, with the p subshell, I can have 3 orbitals. Each orbital can hold 2 electrons, so therefore I can get a maximum of 6 electrons in there. Let's move to the left, the d block. That's actually the transition metals. With the d block, one thing to note, what happens when we get to that first d value is it's not the same number as the row number. It's 1 less than that. So if my row's 4, my d block is actually 3. My row's 5, my d block is actually 4. 6 is 5, 7 is 6. Okay, well, if you remember, the 3d fills after the 4s. So this is a way to predict that we're going to go from 4s to 3d. Okay, so when you get to those transition metals, those d electrons, their n value designation is going to be 1 less than the row number. Okay, how many boxes do we have there? Well, we have 10. Why? Well, because a d subshell can hold 10 electrons. It has 5 orbitals. If you go to the f blocks, you notice technically the row that 4f is in row 6. 5f is in row 7. So for the f's, it's going to be the n value minus 2. And how many boxes do I have for f? Well, I have 14. Why? Because f has 7 orbitals. It can hold 2 electrons each, so we get a total of 14. Now I know this doesn't look like your periodic table directly, because what they do is they take that F block, pull it out, and situate it slightly below the periodic table. But really in the periodic table, that's where the F block is at. Let's look at a picture of a more common periodic table that we're used to seeing. So you can see on this, we've got the S block elements are in blue, the P block are in pink, D block is in yellow, the F block is in kind of a greenish color. All right, but you notice where that lanthanides and actinides, those are the F block, they're pulled down from the middle of that periodic table. Okay, so in row 6 we go 55, 56, 57 to 58, which is the first lanthanide there. Okay, so that little space in there is where those F blocks would go. Okay, so we need to make sure to take that into account as we use a periodic table to fill out electron configurations. Using the periodic table to write out these electron configurations is actually going to be extremely easy compared to trying to memorize the order that these things fill in. You can pull all that information out from the periodic table. All right, so let's look at calcium again. How would we do an electron configuration for calcium? We saw 2 other methods. Well, now looking at the periodic table, where's calcium at? Well, it's at 20. Okay, so what we're going to do is each one of these boxes is going to represent an electron. So if I start with hydrogen, that's 1 electron. I go to helium, that's 2 electrons. That's in row 1. I've just now filled my 1s orbital. So I write my 1s2. I'm still not up to calcium, so I've got to go to lithium and then beryllium. That's the end of my 2s. I filled my 2s, so I've got to go to 2s2. Now I skip that gap, go all the way over to boron, because that's number 5. So I've got boron, then carbon, nitrogen, oxygen, fluorine, neon, because I still haven't hit my calcium. Now I've filled my 2p, so I write 2p6. Go to the next row. 1, 2, I've filled my 3s, so 3s2. Jump across that gap to my 3p, and I keep adding electrons until I get to that calcium. Well, I filled my 3p, so 3p6. So I jump down to row 4s, add 2 electrons, and I'm at my calcium. So I'd write 4s2. Because I'm at my calcium now, that's my electron configuration. I can stop. All right, so using the periodic table is going to actually be a quicker way to write out these electron configurations if you know how to read the periodic table properly. Okay, let's look at another example of this. What if I take the fluorine atom? Fluorine's got 9 electrons, but if I look at this, I'm just going to keep adding electrons until I hit fluorine. Okay, so start with hydrogen. I got 1, 2, that's my 1s2. 1, 2, that's my 2s2. 1, 2, 3, 4, 5, I'm at fluorine, so I'd stop there at 2p5. So my electron configuration for fluorine is 1s2, 2s2, 2p5. All right, let's try a little bit longer one. Say I want to do zirconium. Zirconium's number 40 there. So it's got 40 electrons, so got my 1s2, got my 2s2, got my 2p6, have my 3s2, got my 3p6, still haven't hit my zirconium, got my 4s2. Now remember, when I go from the 4s2, the next set is the D blocks. But the D blocks are going to be the row number minus 1. So the first set there are going to be the 3Ds. Right? But I've got to fill that, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. So that's going to be 3d10. Remember, row is 4, but since I'm in the D block, it's going to be that row number minus 1 and then the D. Okay? When I get to the P's on the opposite side then, those still go by the row number, but I need to fill those. So that's going to be 4p6. Now I'm on to row 5, filled my S, so 5s2. Now I need 2 more electrons to get to my zirconium. Those are in the D block. Row 5 in the D block, so it's going to be 4d, and I've only put 2 electrons in there, so 4d2. And that takes me to my zirconium. Now, I could have done the same thing using one of those other methods that we talked about, where I just count electrons and keep counting up electrons and keep adding electrons to orbitals with higher and higher energy until I run out of electrons. All right, so knowing where those things are at on the periodic table is going to be a quick way to help you identify what electron configurations are. And remember, these configurations are showing us where all the electrons are in that atom, what orbitals are in.